So to make sense of all the reactions we've talked about so far, we first need to be able to balance a redox equation. And this isn't a hard thing to do, but it is an important thing to do because like other balance reactions, you have to know how much of each reactant you put in, and you need to know how much product is going to come out, all that kind of stuff. So this reaction down there is an example of that. It's permanganate, MnO4-, reacting with iron 2+, and a little bit of acid, H+ is added, and the products are manganese 2+, some iron 3+, and 4 waters. So this is an example of a redox reaction. Notice how iron is going from a +2 to a +3, more positive, but the manganese is a little harder to tell. However, if you remember from Chem 221, we talked briefly about what's called a redox number or an oxidation number. And if you want to find out what the oxidation number is of the manganese in permanganate, MnO4-, what you can do is say, all right, the oxidation number of manganese plus 4 times the oxygen's oxidation number, all of that together equals -1. So oxygen's usually -2, -2 times 4 is -8, and -8 from the oxygen plus manganese equals -1. So when you do the quick math there, that's manganese plus 7 in permanganate. And that's all well and great and stuff, but we can use this +7 to confirm that this is a redox reaction. So remember, something has to not only lose electrons, but something has to gain electrons. So if you look at the manganese and the iron on the other side, you have a different story. Manganese is a +2 on the product side, while it was +7 on the reactant side. And the only way manganese can go from a +7 to a +2 is by gaining 5 electrons. So in this case, manganese is gaining electrons, it's being reduced. But something has to be oxidized as well. And you can see there iron 2+ is going to iron 3+. That's going to create 1 electron. The 5 that's in front of the irons is just to make the manganese happy. You need 5 electrons created to make permanganate go to Mn2+. So this is an example of figuring out how to balance a reaction using oxidation numbers, but I'm going to show you an alternate way here that you don't really need to use the oxidation numbers. We'll talk about that here in a little bit. But redox reactions are pretty cool. Here's a video of permanganate, that purple solution on the left, reacting with iron 2+ on the right, and they're going to make the manganese and the iron 3+.
The purple solution is aqueous potassium permanganate. The colorless solution contains iron 2+ ions. When we combine them, a redox reaction occurs. The permanganate ion is reduced to manganese 2+, and the iron is oxidized to iron 3+ ion.
You can see how the purple from the permanganate is now gone, so there's no more MnO4-. And on the product side then, that weird looking liquid there, you've got manganese 2+, which is essentially colorless. Iron 3+ has a very slight yellow tinge, and that's what I see in that beaker. Not a very strong color, that's for sure. However, you can tell that a reaction happened. This is permanganate and iron 2+ going to manganese 2+ and iron 3+. So let's look at some rules as to how you too can balance a redox reaction. It's not too bad. Let's check it out. In this question, we want to know the oxidation number of the vanadium ion in VO2 + 1. So that's a vanadium, that's 2 oxygens, and overall a +1 charge. And you can see the possible charges right there. Well, to answer this one, in Chem 221, we talked about how the sum of the oxidation numbers equals the charge on the ion if there is one. So for this problem, what that means is the oxidation number of the vanadium plus 2 times the oxidation number of the oxygen, which is -2. All of that together equals +1. That's the charge on the ion, so that's why I'm letting that equal +1. So it's like the vanadium oxidation number plus 2 times oxygen equals +1. And in Chem 221, most of the time, hydrogen is +1, oxygen -2, which we'll use here. Fluorine's always -1, etc., etc. Anyway, if we put in here that the vanadium plus the 2 oxygens equals +1, and oxygen is -2, you can see that the vanadium's oxidation number, you can think about it like as an X. And X -4 equals +1. So you put the -4 on the other side is +4. The vanadium here comes out to be +5. So the sum of all the oxidation numbers in a compounder ion equals the charge, if there is one. In this case, that means vanadium plus 2 times the oxygen equals +1. Oxygen's almost always -2. Solving for the vanadium, +5.
Copper metal reacts spontaneously with a solution of silver nitrate. A coating of silver metal forms on the copper, while copper 2+ ions, which are blue in water, are released into the solution.
This is the reaction we looked at earlier where copper metal reacts with silver ions to give copper 2+ and silver. And I'm going to use this as an example of how to balance a redox reaction. Now, truthfully, this is a reaction you could probably balance on your own. It's not too hard. However, it's going to give me a chance to talk about the rules for balancing redox reactions. And if you use these in more complicated examples, you're going to do great. So follow along with me, bear with me. Let's see how we would balance this reaction using these rules. So the first thing you want to do is you just want to divide the reaction into the half reactions. One will be oxidation and one will be reduction. It doesn't really matter if you know what's being oxidized and reduced. But what you do want to do is you want to put like species together. So in the upper right-hand corner there, I've got the general reaction. It's copper and silver plus making copper 2+ and silver. That means you want to put the copper species together and you want to put the silver species together. So I'm going to write copper going to copper 2+ and silver plus going to silver. Now I know, and you can probably figure out that copper is being oxidized and silver plus is being reduced, but you really don't have to worry about that right now. I'll talk about that here in a little bit. So you got the two like species kind of separated into half reactions. Next thing to do, you want to balance them for mass. So you want to make sure that the atoms of copper are the same on both sides and the atoms of silver are the same on both sides, and they are. This one's so simple you don't have to do anything. But sometimes it won't be that simple and you have to balance it. We'll talk about that more later too. But anyway, this is balance for mass. The next thing though, we're going to balance them for charge. And balancing for charge can only happen by adding negative electrons. So in step 3, you want to add negative electrons to the more positive side of the reaction. So as an example of this, copper and copper 2+ is more positive than copper. We're going to add 2 electrons to that side. And you can see then, sure enough, copper 2+, which has a positive 2 charge, and 2 -1 electrons, all of that goes to 0, and that's what the charge is on the reactant side for copper metal. So that's how you balance for charge. You can only add negative electrons. We'll do the same thing with the silver. We need to add an electron to the reactant side, +1 plus the -1 of the electron. That all goes to 0, and that's what the charge is on the product side. So silver is the product, silver plus and 1 electron are the reactants. And notice at this level, we've got one species where electrons are products and one species where an electron or electrons are reactants. And you should always see that here. If you don't see it, something is wrong, all right? So in this case, your copper is losing electrons, it's being oxidized, and your silver plus is gaining an electron to become silver. Silver plus is being reduced. So the oxidized and reduced parts will come out naturally if you've done it right at this step, and you don't have to think back in step 1 or step 2 like what's being oxidized or reduced. All good reactions don't show their electrons. So this step, we want to multiply both of those half reactions by whatever we need to, so that when we combine them, the electrons will cancel out. So the copper going to copper 2+ and 2 electrons is fine, but if you remember, the silver plus only gained 1 electron to become silver. So if we combine those as is, the electrons wouldn't cancel. So let's multiply the other reaction by 2. That means since 2 silver plus reacts with 2 electrons to make 2 silver metals. And now you can see that in the reducing agent part, we have 2 electrons as products. The oxidizing agent part, we have 2 electrons as reactants. So when we add those reactions together, the electrons are out of here, which is important in my chemistry world. So the final step is literally just to add them together. 2 electrons as products, cancel 2 electrons, which are reactants. You've got copper and 2 silver plus, making copper 2 plus and 2 silver, and everything is hunky-dory. However, let's say you get to this part and you're like, oh man, not feeling good about it, man. That's okay, all right? You can absolutely make sure that the reactions are balanced for mass and charge at this point. So for example, for mass, 1 copper metal, 1 copper atom on the product side, no problem. 2 silvers make 2 silvers. So this reaction is definitely balanced for mass. The number of atoms on both sides are the same. But you can also check yourself for charge. So the copper on the left side is 0. Don't have to worry about that. The silver plus is +1, and there's 2 of them. So the whole reactant side is a +2. And on the product side, the 2 silvers don't have a charge, so there's 0. There's a +2 right there. The product side is +2. So this reaction is balanced for charge as well as mass. And again, you can always check yourself if you're feeling uncertain. And I do this a lot myself. So it's a nice thing just to double check, make sure you're good to go. The next example we're going to use involves vanadium. Vanadium's a really cool element. It's named after, I believe it's the Swedish goddess of beauty, Vanadis. I probably am saying all that wrong and incorrectly, but anyway, vanadium is a beautiful metal because it creates just a ton of different colors. So these are just some examples of some vanadium solutions, and you can see it's yellow and blue and green and purple. Oh man, vanadium is pretty cool. So anyway, we're going to use vanadium, not for its color, but for what we can do to learn about balancing redox reactions. In the second example, we're going to balance this reaction in acidic solution. So let's come back to that in a little bit. Now in this reaction, we have VO2 plus 1. That's a vanadium, 2 oxygens, and a +1 charge. And it's reacting with zinc metal, zinc by itself. It's going to make VO2 plus. That's a vanadium and 1 oxygen with a 2 plus charge. And it also makes zinc 2 plus. Okay, so like before, we're going to have 2 vanadium species that we'll put together, and we're going to have 2 zinc species that we're going to put together. But being in acid or base, which is what the third example will be, is going to be important. In acid, you can only have H plus and water. You can add as much of those as you need to. However, H plus and water is what you need to add. So let's see how this works. So first what we want to do is just put the half reactions together. And again, you don't have to know which is being oxidized and reduced. You just want to put the similar species together. So I would definitely put, for example, the zincs together. Zinc going to zinc 2 plus seems reasonable. And then we'll also put the vanadium complexes together. Now earlier in the question, I showed you that vanadium in VO2 plus 1 is a +5. In the second one, the VO2 plus, that vanadium is a +4. So notice it's going from +5 to +4. That means it's gaining an electron. The vanadium species is being reduced. And zinc here is losing 2 electrons to make zinc 2 plus, so that's why it's being oxidized. But again, you don't have to worry about it. Just put the like species together and everything should be cool when you get to the adding electrons part. We'll balance each half reaction for mass, and remember in acid you can only have H plus and water. So the zinc is good to go, 1 zinc on each side, that's not a problem, but the vanadium is definitely messed up. The reactant side has 2 oxygens, VO2 plus 1, and the product side has 1 oxygen, VO 2 plus. So we need to add some oxygen containing species. Now between water and H plus, the only thing with oxygen, of course, is water. So let's start off by adding water to the product side. All right, no problem. But now we have H plus on the product side and no H plus on the reactant side. So in addition to water, you can add H plus ions. This would be the balanced mass reaction for this half reaction. 2H plus plus VO2 plus 1 makes VO2 plus and a water. So you want to add the water to the oxygen deficient side. You add H plus to the hydrogen deficient side when you're balancing these. We need to balance the half reactions for charge, and this is where we're going to add electrons. We can only add negative electrons at this point, but using this, we can make this happen. So zinc going to zinc 2 plus, zinc 2 plus is more positive. We're going to add electrons to the more positive side. If we add 2 minus 1 electrons, that'll balance that positive 2, make the whole product side a charge of 0, and that's what the zinc metal is. So 0 to 0, this reaction is now balanced for charge. The vanadium will do something similar. Now, let's break down the product side first. VO2 plus has a positive 2 charge, and water has no charge. So the whole product side is a positive 2. And if you ignore that electron for just a little bit, VO2 plus 1 is a positive 1 charge. 2H plus, that's 2 times plus 1, positive 2. So you've got positive 2 from the H plus and a positive 1 from the VO2 plus 1. Positive 3. Well, positive 3 on the reactant side does not balance positive 2 on the product side, so we're going to have to add 1 electron to make them balance out. And then if you look at it, minus 1 from the electron, plus 2 from the hydrogens, plus 1 from the VO2 plus, all of that gives you a positive 2 charge, which is what you have on the reduced part. So this is how it works. You just try and add electrons to the more positive side, and hopefully then that will be enough to make everything balance out. You want to multiply by an appropriate factor so that when you add the oxidized and the reduced species together, the electrons don't show. All right, that's pretty important in chemistry. So we'll leave the zinc alone, but the second reaction, we're going to multiply that whole thing through by 2 because we want 2 electrons, not just 1 electron. That way the zinc 2 plus 2 electrons, those electrons will cancel the 2 electrons in the vanadium part and everything will be cool. So I multiplied all of those through by 2 in order to get that answer. So the final step is just adding them together. You're going to have the zinc, you're going to have H plus and VO2 plus 1, and that's going to make zinc 2 plus VO2 plus and 2 waters. And again, you are welcome to check these, make sure they're balanced for both charge and mass, because it's both really important. You have just balanced a reaction in acid. Remember, in acid could mean things like pH less than 7, could be an actual pH number. All of those things would be legit. And again, in acid, only add H plus and water. In this question, we're being asked how many electrons are flowing between the tin and the silver plus. So on the reactant side, you can see we've got tin metal and silver plus ions, and apparently electrons are flowing between those. On the product side, you have tin 2 plus and silver. You can look at tin or silver. I think doing the tin is a little bit easier. Tin is going from a tin 0. Tin solid means tin of a 0 charge. It's going from a 0 charge to a positive 2 on the product side. So that means here that tin is losing 2 electrons to become tin 2 plus. But just because we think they've lost, we should also check the part that's being reduced, and that's silver plus going to silver. So each silver plus needs 1 electron to become silver metal, and there are 2 of them, so 2 electrons are needed to make 2 silver plus turn into 2 silvers. The operative word here is 2, all right? As long as you see that there's 2 electrons being transferred, that's the important part. Usually one species, the oxidized or reduced, is easier. In this case, tin going to tin 2 plus, yeah, it definitely is going to need to lose some electrons, and 2 electrons specifically. And when you think about the stoichiometry, that's why there's the big 2's. It takes 2 silver pluses to gain 2 electrons to make the 2 silver metals.